It was a freezing morning at the Kennedy Space Center in Florida. Loved ones, media, and spectators gathered for this historic launch. Among the crew members for Challenger, a civilian school teacher patiently awaited her departure. She would be giving children a Friday lecture aboard the shuttle only 4 days later. Unfortunately, this lecture would never take place due to the catastrophic disaster occurring only 73 seconds after takeoff. But to understand the errors in risk mitigation that failed to stop this event, we will need to go back to July, 1 year earlier. In July of 1985, mission STS-51F, aka Space Lab 2, took off without any issues. However, further analysis would reveal that the shuttle was nearly doomed at launch. In order to save costs and make the shuttle mission more affordable for payload transportation, NASA would reuse certain components of the shuttle. Following launch, the solid rocket booster, or SRB for short, would eject from the vehicle and parachute into the ocean below. The boosters would then be disassembled and inspected. It was during this routine inspection that members of Morton Thiokol noticed blow-by between seals in the solid rocket motor joints. In a letter addressed to the Thiokol Engineering Vice President, Robert Beaujolais, the project manager of the SRB, expressed his concerns with the O-rings that seal the booster's fuel source. On the Challenger's solid rocket boosters, this seal is located on the aft end of the motor. The seal consists of a primary and secondary O-ring that seals the internal pressurized gases and is intended to prevent the blow-by previously mentioned. It is apparent that NASA was aware of this known issue as a memo sent by Irving Davids, the company's engineer for the Shuttle Propulsion Division, was sent to the Associate Administrator for Spaceflight. In this memo, Irving explains the O-ring erosion problem identified by Thiokol and requests a meeting with NASA's Marshall Space Flight Center to discuss the issue in more detail. Unfortunately, this internal and external communication involving Thiokol and NASA would not be enough. The day before Challenger's launch, Thiokol's director of the SRM project, Alan McDonald, realized that the extremely cold temperatures that night and morning after would have an adverse effect on the two O-rings. He and his team of engineers advised canceling the launch, but following a caucus between Thiokol and NASA managers, the evidence provided was considered insufficient, and the launch proceeded. As Challenger began to lift, with its precious cargo inside, the concerns McDonald and his team had regarding the O-ring began to manifest. As the pressure inside of the SRM started to oscillate, the sections expanded and contracted, rotating the joints. This rotation created larger than normal gaps at the secondary O-ring, and due to the cold temperatures and poor elastic properties, this gap allowed gases to escape. Approximately 70 seconds into flight, the escaping gases ignited and, like a torch to steel, burned a hole into the main fuel tank. Once the leaking fuel ignited, complete breakup of the shuttle was instantaneous. With NASA's lockdown of the operation complete in order to preserve data, a presidential committee was formed shortly after to investigate the accident. Testifying before the committee and the American public, Mr. McDonald gave a detailed report of the events leading up to the mishap. He shared his position he took the day before in order to stop the launch due to the adverse weather conditions. The decision made following a caucus was not what Mr. McDonald was hoping for.
And finally, the conversation concluded, and the recommendation was to proceed on with the launch.
Although not explicitly disclosed in the investigation report, many factors could have been contributed to this catastrophic event. To simply rule the incident as an error in the technical design may limit the point of reference for the complexity of the situation. In the 1980s, NASA was under the microscope in terms of meeting expectations. To summarize, Diane Vaughan, author of Regulating Risk: Implications of the Challenger Accident, a third-party think tank, Mathematica Inc., was called in by NASA to determine how many successful flights per year would be needed to allow the spacecraft to pay for itself. The initial estimate was 30 flights in 1971, but this increased to 60 in 1985. In turn, this forced NASA to make budget cuts that would require an increase in cannibalization of parts. To make matters worse, the focus of individuals was spread amongst multiple responsibilities due to low staffing, causing safety problems to be more passive in nature. With organizations spread across the country, communication breakdown was inevitable.
Were you surprised that some of the top people in the decision-making process didn't know about this at all?
Didn't know about the CIL or the criticality one or what?
Well, the whole thing, the concern on your part and on the part of ICOL's engineers that the original decision had been not to launch and all that.
Oh, I'm very surprised at that. I could hardly believe that. The issue was so controversial, I thought that I'm sure that they were aware of that. I have a hard time believing they didn't.
Pressure on management to meet expectations for flight frequency and reliability influenced members of Thiokol to side against engineering staff to safeguard their responsibilities as managers. Between the pressure to keep up the tempo and the obvious issue of lack of communication to the proper authorities, room for error began to grow. The layers that would have otherwise prevented issues such as this to fall through the cracks were all but completely dissolved. This was in part due to the mixture of organizational factors such as NASA disregarding concerns of Thiokol engineers and socio-cultural factors regarding the international pressures involved in advancing space exploration. Multiple ethical dilemmas presented themselves throughout the development of the disaster. Had they been taken seriously by those who were obligated to act appropriately, the events that unfolded may never have come to pass.
Were you surprised that some of the top people in the decision-making process didn't know about this at all?
Therefore, I'm extremely puzzled why a NASA person could disagree and ask you to review the decision your engineers had reached, since it seemed to me theirs was the responsibility for the design.
Did you ever have an experience where all the engineers voted one way and management voted the other?
It is my honest and very real fear that if we do not take immediate action to dedicate a team to solve the problem, with the field sign having the #1 priority, then we stand in jeopardy of losing a flight along with all the launch pad facilities.
We can find consolation only in faith, for we know in our hearts that you who flew so high and so proud now make your home beyond the stars, safe in God's promise of eternal life. Every family member I talked to asked specifically that we continue the program, that is what their departed loved one would want above all else. We will not disappoint them.